Stoichiometry heat problems are problems where one of the reactants or products is essentially heat. Maybe heat's being absorbed if it's an endothermic reaction, or heat's being released if it's exothermic. And in a stoichiometry heat problem, you relate that to the amount of a reactant that's used up or a product that's generated. So let's take a look at an example and work through it. So here we have a reaction where we're going to burn octane and get water and carbon dioxide. And we see that the heat of this reaction is given as negative 5,430 kilojoules per mole. So negative tells us this is an exothermic reaction, and so heat's being released. And so that's, this is a combustion of a hydrocarbon, so we expect heat to be released. So that all makes sense. And notice that we're given a specific amount of heat for a specific example of this reaction. So we burned a certain amount of stuff and got this much heat released. And the question is how much mass of carbon dioxide is generated when we do that. So the question is, what does this number mean? Kilojoules of heat per mole of what? And the way to read this is to understand that this heat number doesn't really mean anything until you look at the balanced equation. So this means there's this much heat being given off for every 1 mole of this that you burn. Or equivalently, you could say for every 25 halves or 12.5 moles of oxygen gas. Or you could talk about it in terms of reactant. You could say if I generate 8 moles of carbon dioxide, I get 5,430 kilojoules of heat being released. So that's what that unit means. And so you have to read it in the light of the balanced equation. So whenever you see a standard heat of reaction written like this, it has to be written next to the reaction that it's talking about, or it's completely meaningless. Okay, so given that information, let's go ahead and figure out the mass of carbon dioxide generated. So we'll start with what we know. We know that we release 1,200 kilojoules. And since that heat is released, we'll mark it as being negative. It's being extracted from the system. Okay, and then we have to relate that to the carbon dioxide. And because we're doing stoichiometry, we're going to relate that to the moles of carbon dioxide. So our conversion factor is the heat of reaction. So we have 5,430 kilojoules of heat per mole. Well, per what mole? So for 1 mole of this, or for 25 halves moles of this, or 9 moles of this, or 8 moles of CO2. So for 8 moles of carbon dioxide. And so that's going to allow us to cancel our units of kilojoules, and we're going to have units of moles of carbon dioxide, which is what we want. And actually, our final answer, we want to put that into mass. So we need the molar mass of carbon dioxide. So we've got 44 grams of carbon dioxide for every 1 mole of carbon dioxide. So we can cancel that. And now we've got grams of CO2. So now it's just a matter of finding the final answer. So that'll give us 78 grams of carbon dioxide. And when you do a problem like this, it's good not just to check the units, but then also to go and say, does this actually make sense? This says the more heat that we generate, the more carbon dioxide we'll generate. On the other hand, the bigger the heat of the reaction for a given amount of fuel, the less carbon dioxide will generate. That makes sense too. Moles of carbon dioxide are generated per mole of fuel, the more carbon dioxide we're going to generate. So that also makes sense. And of course, the bigger the molar mass, the more this mass will be. So you should do a sort of check to make sure that everything's on the top and bottom as you expect. The units will get you most of the way there, or even all the way there most of the time, but you should double check if it makes conceptual sense as well. So that's our answer. So we were able to relate the amount of a product to how much heat was given off in the reaction.